Right, so when you're doing sliding stuff, we assume that all the objects are particles, so all the forces act at one point and all the movements are in a straight line. We're going to now think about things turning, and we can treat objects as rigid bodies, so they do actually have a size. So we choose a pivot point and then we measure the effect of the force using its moment. Okay. Right, so a moment, you do the perpendicular component of the force multiplied by the distance to the point at which you're taking moments, or if you find it easier, you can pretend that the point you're taking moments about is the centre of the universe, and you do the full size of the force times the perpendicular component of the distance. We'll see on an example. For every single question, sketch it, draw on the forces, draw on the distances, and then you can resolve and you can take moments. I do anti-clockwise minus clockwise equals 0. Some people do anti-clockwise equals clockwise. Okay. Two things that we haven't seen on any past exam questions that are on your syllabus are 2D shapes. So look at one of those, and also finding the total moment rather than having things in equilibrium. Every exam question has been equilibrium. Okay, so this is just from your textbook. So we've got a two-dimensional shape here made from plastic sheet, and we're told it's got weight 40 newtons. So the diagram's already given for us. It's told it's 40 newtons, and we're going to assume it's a uniform laminar. So uniform means we've got equal density throughout, so the weight is going to act right at the centre. Oops. It's approximately the centre there, and that's 40 newtons. Okay. Right. We've got some wires, and they're holding it in place. If the sign can be modelled as uniform laminar, that just means a flat shape. And we've got our distances, so AB is 0.5 metres. Okay, and AD is 0.4 metres. Okay, we need to find T1, T2, and T3. Okay, well I can see that I've got 2 vertical forces, 2 horizontal. So the easiest way of finding this T1 is going to be resolving rather than taking moments. So let's resolve vertically. Okay, so upwards we have got T1. Okay, and against that we've got our 40 newtons. We're using F equals ma when we resolve. There's no acceleration, so that equals 0. So T1 is 40 newtons. Okay, so now if we look at wanting to find T1 and T2, we can see that if we resolve horizontally, then T3 minus T2 would equal 0, just using F equals ma again. So we know that they're equal to each other. So if we find one, we find them both. So then to find them, we want to take moments. So the way to take moments is you usually choose the point that's got the most forces acting on it that you don't know. So that's going to be point A. So we're going to take moments at point A. Okay, and I'm going to go around my forces. I'm going to take positive to be anti-clockwise and negative to be clockwise. So if I pull this way, if I imagine my sign and I start pulling this way, it's going to have a tendency to move anti-clockwise for T1. So T1's going to be positive. So I've got T1. And I need to do the force times the perpendicular distance. So if I extended the line of action of that force, it's not very lined up, you can see it would cross, kind of imagine that A is our origin and these are our axes, it would cross the axis down here. So the distance to our force is going to be 0.4. Okay, so we're imagining that A is the centre, our origin, and we want to see where does our force, line of action of our force, cross one of those axes, and it only crosses this axis at a distance of 0.4. So now we do exactly the same for the 40 newtons. Okay, so I've got my 40 newtons. If I pulled on the weight about that pivot point, so you can imagine having a little split pin there, and you're pulling the laminar, we're going to be acting clockwise. Okay, so we're going to have a minus for this one. There's our centre. Look at our line of action of our weight. Okay, and that would cross just this axis. It would cross the AB line at this distance here, which is going to be 0.25 metres. So that is 40 times 0.25. Okay, and that has to equal 0 because it's an equilibrium. The anti-clockwise and clockwise forces and moments balance. Okay, so you can solve that, and that, sorry, that was T, that's not T1, that's T3. So you can solve that to get T3 and substitute it back in to get T2. Okay, that's easy, so I'm going to skip. Right, this is again from your textbook because I haven't seen any examples like this. So we want to sketch what's going on first. What we've got a diving board, okay, which is 3 meters. Okay, there we go. And we've got a mass of 100 kilogram. It's a uniform plank, so we can assume that weight is acting right in the middle. Okay, so it's 100 G. And the distance then is 1.5 meters. Okay, and then we've got a diver of mass 70 kilograms is at one end, so there he goes. 70 G will be his weight, and he's right at one end, so we know that distance is 3 meters. Find the total moment around the opposite end of the board. So we're going to find the total moment about this point here. Okay, so moments about X. So going anti-clockwise, we have absolutely nothing at all. Okay, so we've got going clockwise, we've got the 70G times by 3 meters, and we've also got going clockwise 100G times 1.5, and that is, we have to say it clockwise because we're asked for the total moment. So obviously you can simplify that and work it out. Okay. Then finally, part B, explain how you use the fact that the plank is rigid in your calculation. So we've assumed that it can't bend at all. Okay, otherwise we would have to have different distances measured.